talking about limiting reactant. Before I get into the nitty-gritty and all the chemistry behind limiting reactants, I'd like to give a really quick example of a real-life scenario that helped me a lot while I was studying limiting reactant. So I'm sure many of you guys are familiar with sandwiches. In order to make a sandwich, you need 2 slices of bread. And yes, this yellow blob is my best drawing of a piece of bread. But anyways, let's continue. So you need 2 slices of bread and you need some type of filling inside of that bread. Let's say we're making a tomato sandwich. So we really only need 1 slice of tomato in between. And then once you combine both of those, you get eventually 1 whole sandwich. And so you have your first slice of bread, first slice of tomato, and then your second slice of bread. So now, let's say we ran over to the store and we were only able to grab 4 slices of bread and 3 slices of tomato. And we sit down to make our sandwiches because we're extremely hungry once we come back home. So now we're making our first sandwich right here. So our first sandwich is our first slice of bread, first slice of tomato, and then our second slice of bread. So now after we make our first sandwich, we see that we have 2 slices of bread left, and we also only have 2 slices of tomato left. Perfect. So now we're going to make a second sandwich because we're pretty hungry. So we make a second sandwich right here. Our first slice of bread. Actually, this is our third slice of bread. Our second slice of tomato. And our fourth and final piece of bread. So now when we look at the amount of resources that we have, we see that we no longer have any slices of bread and we have 1 more slice of tomato. Now, if we really wanted to, we could try to make another sandwich, but we realized that we don't have any more bread, and so we see that this doesn't really work, and we have no more sandwiches left. And so clearly that makes us really sad because we wanted to eat more sandwiches, but we didn't have enough resources. We were limited by the amount of bread that we had. We had enough slices of tomato, so that's our excess, but we were limited by the amount of bread that we had, and that, in essence, is the general concept of limiting reactant. So now, let's dive right into some chemistry. Let's look at our earlier reaction of combustion of methane. We can see some similarities here between the reactants of this combustion reaction and the reactants of this sandwich reaction. So here, if you look right here, we have a stoichiometric coefficient of 2 for these slices of bread. And similarly, we have a stoichiometric coefficient of 2 for our O2. So I'm going to put that in yellow to kind of relate it to our slices of bread. And our other reactant, tomato, had a stoichiometric coefficient of 1 right here. And similarly, if we look right here, we see that we have a stoichiometric coefficient of 1 for our CH4. And I'm going to put that in red right there for our CH4 to relate it to our slice of tomato. So much like our sandwich reaction, chemical reactions also work in a very similar way. So now let's get into a problem that will help us kind of visually see the amount of product that we can get from a limiting reactant reaction. So below, I've written down a neat problem. Let's say we're given 2 grams of CH4, and at the same time, we're also only given 5 grams of CO2. Sorry, of O2. And the question asks, how many grams of CO2 will I produce? Perfect. So now, let's go ahead and solve this problem. The way we like to attack limiting reactant problems is by running dimensional analyses on all the reactants that we're given. And eventually, once we run dimensional analysis, the goal is to see which type of reactant, whether it's the O2 or the CH4, will produce the least amount of product. Because whichever one produces the least amount of product is the one that will run out the fastest, just like our slices of bread. So now, let's begin with our first reactant, CH4. So on the left side of my screen, I'm going to write 2 grams of CH4. And we eventually want to get our final product of this dimensional analysis problem into grams of CO2. That's the big goal at the end of it. So let's continue with our problem. So the first step that we need to do is go from grams of CH4 into moles of CH4. So we run a conversion factor sorts, and we see that for every mole of CH4, you have 16 grams. So now we need to go from moles of CH4 into moles of CO2. So we look towards our combustion reaction problem to see our conversion factor, and we can see that for every 1 mole of CH4 right here, you get 1 mole of CO2. So now let's go down and write that down here. So for every 1 mole CH4, you get 1 mole of CO2. And finally, we convert our moles of CO2 into grams of CO2, which is the final product that we want. So we get 1 mole CO2, and if you look at your periodic table, you can calculate that 44 grams are in 1 mole of CO2. So now we perform the calculation, and we see that we get, in the end, 5.5 grams of CO2. And of course, all our units cancel out. Like in our previous video, moles of CO2 cancel out with moles of CO2. Moles of CH4 cancels out with moles of CH4. Grams of CH4 also cancels out with grams of CH4. So in the end, we're left with only grams of CO2. Perfect. So now that I've gone through the first dimensional analysis problem of 2 grams of CH4, why don't you pause the video and try doing the other dimensional analysis problem for 5 grams of O2. Okay, welcome back. I hope you were able to take a break and finish the problem for 5 grams of O2. So now I'll go ahead and write out the solution for it. So first, we need to take 5 grams of O2, convert that into moles of O2. So what you get is, for every 1 mole of O2, you have 32 grams. Now you multiply that by, you need to convert from moles of O2 into moles of CO2, and we see that the conversion factor right here is that for every 2 moles of O2, you get 1 mole of CO2. So I'm going to go ahead and write that down right here. 2 moles of O2 for every 1 mole CO2. And now we need to go from moles of CO2 into grams of CO2. So as I wrote in the previous problem, for every 1 mole of CO2, you get 44 grams of CO2. Now let's run the calculation. So what we need to do is we need to do 5 times 44, and then divide that by 32. Divide that by 32 times 2. So now what that gets you is 3.4375 grams of CO2. So now let's compare the amount of product that we've gotten from both sides. So in a column right here, I'm going to write the 2 grams of CH4. And In the other column right here, I'm gonna do 5 grams of O2. And we see that for the 2 grams of CH4, we got 5.5 grams of CO2. I'm gonna write that right here, 5 grams CO2. And for the 5 grams of, sorry, not 5 grams of O2, 5.5 grams CO2. And then for the 5 grams of O2, we see that there you get 3.4375 grams of CO2. So just by comparing the amount of product we get, we can see that the winning reactant is CH4. And the one that runs out the most, the one that runs out the quickest is the 5 grams of O2. So now we can say that our limiting reactant is the 5 grams of O2 in this scenario. As a quick side note, I do want to say that it's not always guaranteed that O2 or any reactant that has a stoichiometric coefficient greater than the reactant that you're comparing with, so in this case O2 had 2 as the stoichiometric coefficient, it's not always guaranteed that that reactant is always going to be the limiting reactant. You should always perform the calculation to see which one is the limiting reactant. So let's say I changed this problem a little bit to say that instead of 5 grams of O2, I reacted 2 grams of CH4 with 10 grams of O2. So if you perform the calculations, you're eventually going to see that with just 10 grams of O2, you get 6.875 grams of CO2. So now if I go down here and I compare 6.875 grams, let me write that down, 6.875 grams of CO2, we see that the result changes, and now the winning product out of this is the 10 grams of O2 instead of the CH4 like in the previous problem. So it totally changes which one is the limiting reactant depending on the amount of each reactant that you have. So you should always perform the calculations, always perform the dimensional analysis problems to see which one you produce less, and not just go by which one has a greater stoichiometric coefficient. So that wraps up this video. Thanks for watching, and I'll see you in the next one.